I now call to order the lecture portion of the 2517th meeting in what is now the 154th year since PSW was founded on March 13th, 1871. Good evening, everyone.
Good evening.
And my name is Larry Milstein. I am the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to the lecture part of today's PSW meeting and to the lecture by Alex Creely on commercial fusion power. First, let's thank our sponsors. 2024-2025 full-year sponsor, Mike Helton and Helton Associates, LLC. Thank you, Mike. We are forever grateful. Series sponsor, PSW member Joe Schulman. Thank you, Joe. Please join me in thanking them all for their generous support. The Society needs your support to meet its expenses for the year. So if you've not given or feel you can give more than you have, please don't hesitate to donate. If you have any questions, please let me know. I am pleased to announce the following new member, tonight's speaker, Alex Creely, who learned of PSW from our invitation to him to speak here tonight, and whose interests will certainly be clear in a fair measure from his lecture tonight. All members are invited to the pre-lecture receptions and dinners with the speaker for camaraderie and interesting discussion. If you're interested in membership, you can access a membership application on the PSW website by clicking on the blue Join button on the home page at the upper right-hand corner. Or if you're here in the Powell Auditorium, you can use the QR code on the business cards on the tables at the back of the room. Everyone who has a genuine interest in science is eligible to be a member of PSW. Please join. Recording Secretary Scott Matthews will now present the minutes of the 2516th meeting and the lecture by Mark Palmer on muon colliders.
Thank you, Larry. Good evening, everyone. On May 30th, 2025, members of the Society and guests joined the speaker for a reception and dinner at 5:45 p.m. in the members' dining room at the Cosmos Club. Thereafter, they joined other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2516th meeting of the Society to order at 8:01 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, announcing new members, and inviting guests to join the Society. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Carrie Liss, titled Real-Time Observations of Early Solar System Evolution. The minutes were approved as read. President Milstein then introduced the speaker for the evening, Mark Palmer of the Brookhaven National Laboratory. His lecture was titled The Path to an Energy Frontier Muon Collider. The speaker began by saying that particle physics is the exploration of the subatomic particles that make up our universe and the laws that govern their interactions. He briefly described the groups or families of subatomic particles, quarks, leptons, bosons, or force carriers. Palmer described the types of high-energy physics particle colliders currently in operation, giving examples of each type. These included proton-proton or proton-antiproton colliders, electron-positron colliders in both linear and circular configurations. He presented the so-called Livingston plot, showing the increase in collision energy as a function of time from the 1970s to the present day, as well as projections of possible future colliders. The speaker provided an overview of multi-TeV machine concepts. These included TeV-class conventional linear colliders, proton-proton energy frontier machines, lepton-ion machines, and lepton-lepton energy frontier machines. He showed schematic diagrams and gave details about some of the potential designs of a proton-proton collider. These included the Future Circular Collider, or FCC, with a circumference of 100 kilometers and a center of mass collision energy of 100 TeV and 6 Tesla dipoles. The SPPC, a Chinese version of the FCC, also with a circumference of 100 kilometers, a center of mass collision energy of 125 TeV, and 20 Tesla dipoles. And the, quote, collider in sea, which would be constructed underwater in the Gulf of Mexico, or perhaps the Gulf of America, with a circumference of 1,900 kilometers and a center of mass collision energy of 500 TeV and 3.5 Tesla dipoles. Palmer then discussed energy frontier lepton colliders, including muon colliders and Wakefield accelerators. He discussed the technical maturity of each of these approaches, indicating that, quote, almost none of these machines are ready for construction today, end quote. The speaker then discussed the potential advantages of a muon collider. These included intense cold beams, which enable measurement of lepton flavor violation, anomalous magnetic moments, and act as a precision source of neutrinos. New opportunities in high-energy physics by providing strong coupling to the Higgs boson, reduced synchrotron radiation, and beams with a very narrow energy distribution, and collider synergies in the areas of long baseline neutrino experiments and material science. Palmer discussed some of the challenges associated with muon colliders. These included the short lifetime of the muons, the ionizing radiation from neutrinos, the need for a liquid target, and the decay particles which must be distinguished from the collision products. He gave an equation for the luminosity of a muon beam, indicating that for a 10 TeV accelerator, there would be about 2 times 10 to the 12 particles per bunch, occurring at 5 bunches per second in a 1 micron diameter beam, resulting in a luminosity of approximately 10 to the 35 per square centimeter per second. The speaker discussed the history of muon colliders, saying that the idea was first proposed in 1969 and further developed in 1996 at the SNOMAS meeting. During the 2000s, the concept of combining muon colliders and a neutrino factory was discussed, and in 2010, the Muon Accelerator Program, or MAP, was proposed in the United States. In 2014, the MAP effort was ramped down, largely due to interest in the neutrino and the Higgs boson. In 2018, a renewed interest in muon colliders was expressed in the European Particle Physics Strategy Update. In 2023, the US P5 report emphasized the need to explore a 10 TeV collider and the so-called muon shot. Palmer showed a schematic diagram of a proposed muon collider. It consisted of a proton driver, a front end with a target and buncher, an ionization cooling stage, an accelerator stage, and a collider ring. He claimed that this type of collider could provide an energy-efficient route to the 10 TeV energy frontier. The speaker ended his talk by discussing several of the technological developments that would be required to ensure the feasibility of a muon collider. He said that the community is aiming for a reference design by the end of the decade. The lecture was followed by a question and answer session. A member asked about the ionizing radiation produced by neutrinos. Palmer responded that while neutrinos very rarely interact with matter, the intensity and energy of the neutrinos from a muon collider would be sufficient to cause ionizing radiation and could therefore constitute a health hazard. A member on the live stream asked how many Higgs particles have been generated and observed, and how do those numbers compare to a, quote, Higgs factory? Palmer responded that he didn't know the exact number, but the idea of a Higgs factory was to dramatically increase the number of particles observed and not necessarily to increase the number being produced. A member asked about the benefits a muon collider could provide the material science community. Palmer responded that muon spin resonance studies are of particular interest to materials scientists, and that there are currently very few machines capable of making such measurements. After the question and answer period, President Milstein thanked the speaker and presented him with a PSW rosette, a signed copy of the announcement of his talk, and a signed copy of Volume 17 of the PSW Bulletin. He then announced speakers of upcoming lectures and made a number of housekeeping announcements. he adjourned the 2,516th meeting of the Society at 10:01 p.m. Eastern Time. Temperature in Washington, D.C., 17.8 degrees Celsius. Weather, partly cloudy. Audience in the Powell Auditorium, 33. Viewers on the live stream, 38, for a total of 71 viewers. Views of the video in the first 2 weeks, 336. Respectfully submitted, Scott Matthews, Recording Secretary.
Thank you, Scott. Are there any comments or corrections on the minutes? Hearing none, I will entertain a motion to accept the minutes as read. Do I have a second? All members in favor? All members opposed? Hearing none, the minutes are unanimously approved and will be posted to the website unless we get a comment from our online viewers with an important and necessary correction. We now turn to tonight's lecture by Alex Creely. Alex is the chief engineer at Commonwealth Fusion Systems. He leads the technical design of ARC and leads the Tokamak operations group, preparing tools and teams for the operation of SPARC, which will be the world's first commercial fusion reactor. Alex's doctoral work at MIT focused on building and operating specialized instrumentation on tokamaks at both MIT and the Max Planck Institute for Plasma Physics in Germany. And he spent time working on a accelerator at the National Institute for Fusion Science in Japan. He's the lead author on the papers laying out the physics basis for the SPARC tokamak. Alex earned a BS in mechanical engineering at Princeton and a PhD in applied plasma physics at MIT. All questions will be fielded after the lecture in our Q&A session. Alex, the stage is yours.
Thank you very much for having me. My name is Alex Creely. As Larry said, I'm the chief engineer for ARC Design and the director of Tokamak operations at CFS. So I'll tonight talk about fusion pretty broadly, a little bit about what is a tokamak, what is this type of fusion machine we're building, a little bit about CFS as a company, like our specific piece of the technology, our path forward, and a little bit, next steps, next challenges, bringing fusion from what it currently is, which is science and a experimentation, to hopefully a commercial source of electricity in the very near future. So hopefully, I'll dive into it. I will say I have started, fairly basics with the basics of fusion, but hopefully we'll dig into some of the details pretty soon. So why am I here talking about fusion? I think it's fairly broadly accepted that the world needs some new energy, new sources of energy. A huge number of different places have projected how much new clean energy we're going to need in the next couple of decades. The short version is all of them say a lot, and this is going to be a huge change in how humanity produces energy, a huge change in industry. So we think there's something important coming, a big change in how the energy economy works. Why specifically am I going to talk about fusion? So I won't talk too much about what fusion is, but before I dig into it, fusion as an energy source could be hugely disruptive in the energy space. It's clean, doesn't produce any carbon emissions, it doesn't really produce any kind of other toxic output. It's firm, so it's on when you want it, it's off when you don't need it. It's safe, it's scalable, so you can build it very rapidly anywhere around the world, and it's secure, so you don't have supply chains of gas or oil or something that you need to import from all over the place. So as a high level, why are we working on fusion at all? The short version is if you can get it to work, it's hugely beneficial in just producing energy and other electricity around the world. So I'll with that as the basis of why are we interested in fusion, I'll talk a little bit about what is fusion, what is the basic process, and I'll talk about this state of matter called a plasma, and that I'll talk about that why are we interested basically. So what is fusion? Brief review. I know people know this, but I'll say it anyway. All matter is made up of atoms. I draw a gold bar here because it's interesting. You zoom in, atom is a nucleus and a bunch of electrons. That's not the right number of electrons for gold, but I got board of drawing dots. You zoom in further to the nucleus and you get protons and neutrons. So here I'm showing blue dots as neutrons and red dots as protons. Also not the right number for gold, but close enough. Before I talk about fusion, I'll talk about fission. So any, quote, like nuclear power today is fission. You take a big atom like uranium, you hit it with a neutron, it splits into multiple smaller atoms, that releases a bunch of energy. And by releases energy, we mean the products are moving quickly, so they have kinetic energy, eventually that turns into heat, and you can use that to make electricity. Fusion is the opposite. So you're taking small atoms and combining them. And so mostly I'll talk about fusion of hydrogen isotopes, specifically deuterium and tritium. So deuterium is a hydrogen with 1 neutron, tritium is a hydrogen with 2 neutrons. If you smash those together really hard, they will fuse, they will combine into helium-4. So helium, moving fast, has a bunch of energy, and a free neutron. So that neutron comes out also with a bunch of energy. By smash them together really hard, I mean get it really, really hot. And by really hot, we mean something like 100 million Kelvin. So I saw in the previous lecture, you're talking about TeV, tera electron volts. In electron volt units, this is like kilo electron volts, so tens of kilo electron volts. So not quite as fast as a particle accelerator, not quite that high energy, but very, very high energy by like basically any like normal standards of moving around with normal temperatures. And where do you see that normally? Normally, you see that in the stars. So most of the energy in the universe comes from fusion. The sun and all the stars are fusing. That's where they produce all their energy. And so, like unsurprisingly, if you look for something that's going to be 100 million degrees, typically the easiest place to find it would be a star. If you make anything that hot, so anything that's going to be 100 million degrees, you will have the state of matter that we call a plasma. So I'll talk a little bit about like plasmas and what they are and why we're interested. Not just as a purely scientific pursuit, they are interesting from a physics perspective, but we're interested in making plasmas because in order to do fusion, you need to make a plasma. You need it hot, and anything that hot will be a plasma. So what is a plasma? It's state of matter. Here I'm drawing dots. Now the purple dots are atoms. So a solid, you have stuff stuck together. The atoms don't really move around very much. Maybe they vibrate a little bit. You heat that up a little bit, they start to move around as a liquid. So there's like liquid water, so 273 Kelvin, 32 Fahrenheit. Heat it up even more, you get a gas. Now the atoms are kind of flying past each other, so 212 Fahrenheit, 373 Kelvin. If you heat that up even more, you actually separate out the electrons from the ions. So rather than having atoms moving around, you separately have electrons moving around and the positively charged nuclei, the ions, moving around. And depending on what material you're looking at, it's something like 10,000-ish Kelvin. So different for hydrogen versus helium versus something else. But order of magnitude, 10,000 Kelvin, you start to get a plasma. You can make anything into plasma. You can have an iron plasma if you really want to, if you really want something hot enough. But typically, you start with gases. Those are the easiest to ionize and turn into a plasma. So we're interested in a plasma because if you want to do fusion, you need something hot. If it's going to be that hot, it will be a plasma. 10,000 degrees sounds a little bit esoteric, but there's actually a lot more plasma around us than most people would think. So I already mentioned stars are plasma. So something like 99% of the observable universe is plasma. I know, dark matter, separate thing, not observable yet. But of the observable universe, a huge fraction is plasma. The northern lights, the aurora borealis. I don't know if you could see it down here this past year in Boston. You could just kind of see the northern lights. So that's very small amounts of plasma, like way up in the upper atmosphere. Lightning is a plasma. Again, I apologize my Boston picture, but you have to forgive me. Lightning's a plasma, and actually neon signs. So a neon sign is a little tube with a tiny, tiny bit of typically neon, like the element in it, that will actually ionize when you turn on the tube. And actually, neon itself is typically like a red-orange color, and if it's a different color, it's actually a different element in there. It's not actually neon, even though you call it a neon sign. You might say, like, wait a second. You said this was 10,000 degrees. I'm pretty sure I can go touch that neon sign. It's probably hot, but it's not that hot. It's a good question. It turns out that the density of the element in there, density of neon, is so low that even though each individual particle has a lot of energy, so it's hot, the total amount of heat transfer to the little tube is not that much. So the tube will be warm, not crazy hot, but all the particles in there are pretty high energy, so high temperature. So neon is a plasma, even though it doesn't seem like it's something that's 10,000 degrees. Actually, fluorescent light bulbs too are a plasma in there. So maybe going back briefly, plasma is interested. We want to do fusion, have to make something hot. Anything that hot will be a plasma. I'll talk now a little bit about tokamak. I'll explain what this word means as well in a second, but the short version is like this is a type of fusion machine. So I'll explain this plot in a second, but basically there's a whole bunch of different types of fusion machines in the world. You typically measure how good is your fusion machine. We have some plasma out there probably, making some noise. Yeah, intentional sound effects here, it's great. You typically measure how good is your fusion machine by the product of three quantities, very creatively called the triple product. Is the temperature, how hot is your fuel, needs to be hot. The density, do you have enough fuel? If you don't have enough, you're not really going to make much power. So like particle accelerators, for example, have incredibly high energies, but very, very, very low density. And then the confinement time, so this is the characteristic timescale by which energy leaves the system. You can think of it like insulation, like how well insulated is your fuel. So on this plot here, the vertical axis, the y-axis, is density times confinement time with the nice units of seconds per meter cubed. And then the x-axis, the horizontal axis, is temperature in keV, kiloelectron volts. And like the short version is you want to move up toward the right. Up toward the right is net energy production, where you produce more energy than it takes to heat the plasma. And yeah, so this plot has a whole bunch of different types of fusion machines on it. The red dots are tokamaks. The black X's are laser machines, like the National Ignition Facility in California. The green stars are stellarators, so like it's a twisty donut, which I'll talk about later. And there's a whole zoo of like other types of fusion machines out there. And this just to give a sense of like the different, like the variety of fusion machines you can do. Yes. Right, and so you want to move to the upper right. And so like this area up here is where you want to move for net energy production. And I'll say we CFS, I'll talk more about the company later, have chosen to use a tokamak, not just because it's our favorite, but because the world has built more than 100 of this type of machine. And so the physics of how does a tokamak operate is reasonably well understood. There are still questions out there, but like on the whole, reasonably well understood how it works. I'll say not all 100 tokamaks are on here. This doesn't include all the data points, but there's quite a lot of them. And as Larry mentioned, I did part of my PhD work on the Alcator CMOD. It says CMOD here, tokamak, those couple dots, and then ASDEX upgrade, the one in Germany, a little bit below it. So you've worked on a couple of these. And the goal of this is to get to net energy production, or a gain Q of greater than 1. Great. So what is a tokamak? As I said in fusion, you have to get your fuel hot, and so you need to confine the energy somehow. Stars do this with gravity. They're very big. They hold in all the energy that way. Unfortunately, to do that, you need like 1 star worth of mass. We do not have that on Earth, so we will have to come up with some other way of holding in the fusion energy. And so we will use magnets. So the fundamental property of charged particles, the Lorentz force, if you have a magnetic field, which I draw here in pink as these pink arrows, a charged particle, either negative or positive, will orbit around it. So it'll orbit around the magnetic field, so it can move along the field. It can't move across it other than in these orbits. Sounds good? I'll also draw some electromagnets now. So these gray things are my little cartoon of an electromagnet going around making a magnetic field. That'll make a bunch of straight magnetic field. You put some particles in there. So my ions and electrons moving here this way. Sounds good? So these particles now won't touch the magnets, but unfortunately, they will still leak out the ends. So like they can move along the magnetic field, so they just leak out the ends. And yeah, it's a really, really long linear device. Fortunately, people are clever. You put it in a circle. Circle doesn't have any ends, so now I'll show these magnets here, a magnetic field going around in a circle like this way. And just, I know most people know this, but the math word for donut-shaped is a torus. So these are toroidal field coils. They make a donut-shaped magnetic field. Unfortunately, and I'll draw some unfortunately, it's a little more complicated than that. I'm now going to stop drawing individual particles and just draw an orange blob. A plasma is a fluid, so you can approximate it like a big blob. Unfortunately, it's a bit more complicated than that. And this plasma wants to expand out radially. There's a couple reasons for this. The biggest one is just like, it's like a bicycle tube when you're pumping it up. It wants to expand radially because it has a finite pressure, a fluid pressure. And just geometrically, there is more surface area on the outside of that than on the inside. So the tube wants to expand outward. So the same thing, plasma wants to do the same thing. So it has this tube here. It wants to expand outward radially. And we confine that in the tokamak geometry with, surprisingly, more magnets. We have a magnet in the center that we call the central solenoid. Pointers, not intuitive. Central solenoid, that's this cylinder here in the middle. A solenoid is a name for a long, skinny magnet. It's in the center. And then we have poloidal field coils. These are these larger gray ones that go around this way. And the poloidal is just like if you take a slice of the donut, that plane, that view of it is called the poloidal plane. So they make a magnetic field in that plane, so they are called poloidal field coils. What do these things do? The central solenoid drives an electrical current around the plasma. It effectively operates like a transformer, an inductive transformer, where the central solenoid is the primary of the transformer, and the plasma is a one-turn secondary of that transformer. And the poloidal field coils use additional magnetic fields basically to like push the plasma back inward radially, so to keep it in the right radial location. This is the basics of a tokamak. So a tokamak, basically by definition, is a set of toroidal field coils, some kind of thing to drive current, typically a central solenoid, and a set of poloidal field coils to keep the plasma in the right radial spot. And tokamak, the word itself, is actually a conglomeration of a bunch of Russian words. I don't speak Russian, I'm sorry, but it was toroidal magnetic chamber, something in Russian, all squished together, became tokamak. So this is the original T3 tokamak back in the 1950s in the Soviet Union. But the world's built a bunch of these. So this was the Alcator CMOD tokamak at MIT. This is the ASDEX upgrade, the tokamak, the one in Germany that I worked at. And this is, to date, the highest performing tokamak in the world, called JET, the Joint European Torus, that was just outside of Oxford in the UK. Recently shut down after operating for about 40 years. But just to give a sense of scale, there's some stairs back here. So like, it's a big one. But it's a fairly large facility that got very, very high plasma performance. So that's a little bit on the background of like, what is fusion, what is a plasma, why are we interested? There's a bunch of different types of fusion machines. I won't talk about all the other types of fusion machines. There is a zoo. But a bit about what is the tokamak and why am I talking about tokamaks here? So now I'll talk a little bit about the company, Commonwealth Fusion Systems, where I'm from, and like a bit of like how are we planning on getting to a commercial fusion power plant. So who are we as a company? We were founded in 2018, so we're only about 7 years old. I've been there 6 years, so I started as lucky number 13, still there, so can't have been that bad. And we spun out of MIT. So we came out of the fusion lab at MIT. We still have very close connections with MIT, but now we've grown quite a lot since then. We've raised more than $2 billion in venture capital financing. So we have a little bit of federal government money from the Department of Energy, but it's less than 1% of that. And the large majority of our funding comes from venture capital. So everything from large oil and gas companies like Eni in Italy and Equinor in Norway to more traditional venture capital firms, Breakthrough Energy Ventures, Coastal Ventures, large companies like Google, hedge funds like Coatue and Tiger Global, and sovereign wealth funds like Tokamak from Singapore. So very global, pretty wide range of investors. We have a large, high caliber team. We're more than 1,000 people now, which is kind of crazy. When we've increased in size by 100x in 6 years. So it's been quite the adventure. What is our path? So at a high level, our goal is to take the relatively well understood physics from tokamaks. There are still open questions for sure, but relatively well understood. And combine that with a fundamentally new magnet technology. So tokamaks are big magnetic bottles. Unsurprisingly, if you can build a better magnet, you can build a better tokamak. We combine those together into a tokamak. This is a commercial demonstration. It's not yet a full commercial power plant, but it shows the basic technology. It produces net energy. We call this SPARC, that is now under construction. And then the next step is ARC, which will be a commercial power plant, and I'll talk more about that a bit later. But that'll be an actual commercial product, sit on the electrical grid, make electricity, power houses or industry or whatever. So a bit of background. R&D, more on the R&D side, physics. We publish very regularly in academic journals, and I think the extent of when we say the physics is pretty well understood, and also we're open about it, we publish in peer-reviewed journals all of the physics basically describing if you could build this machine, let's say magic, you can somehow figure out the engineering and construct this machine, would it produce the plasmas that we say it will? And we try to be very open about that. So we published a series of papers in the Journal of Plasma Physics in 2020. This was like the original physics basis. We've continued to publish in a bunch of other journals, so nuclear fusion, physics of plasmas, plasma physics and confined fusion or controlled fusion. And we've also continued to actually publish some of our magnet discussion in the IEEE Transactions on Applied Superconductivity. So when I say we have known physics, like the physics of tokamaks in general are well known. People built 100 of these, and then we're very upfront about like why do we think this thing will work if we can build it. We also work with a lot of partners. So I wore a red shirt so that you could recognize me from my the announcement as well. But we work with a lot more than 100 physics collaborators from different institutions around the world, MIT, Columbia University, Oak Ridge National Lab, Princeton Plasma Physics Lab, EPFL, École Polytechnique Fédérale des Lausanne in Switzerland, Germany, Finland, Netherlands, all over the world. This is like very much on the physics side of things. So we want we want to work with the best experts in the world to get this thing done. We want to basically find areas where academic institutions and us, a private company, can have the most, best ability to complement each other's skill sets and work in those areas. Magnet technology. So as I said before, tokamaks are magnetic bottles. The confinement time, so the rate at which heat comes out of the plasma, largely is driven to 0th order by the size of the orbit of the particle around that magnetic field, the gyro radius or the Larmor radius. It's a bit more subtle than that, but like to 0th order, it's like how many radii, how many Larmor radii can you fit in the size of the machine? So that would mean if you want more radii, more orbits within the machine, you either need to make the machine physically larger, just to have more of them, or you need to make the magnetic field stronger, because the size of that orbit is inversely proportional with the magnetic field. So the higher the magnetic field, the smaller the orbit. Up until, let's say, 10 years ago, the best superconducting magnet you could make at this scale could make a field at the center of the plasma of like maybe 5 or 6 Tesla. And for context, like the biggest magnet most people would ever interact with in like normal life would be an MRI machine. That's like 1.5 Tesla ish. There's higher field ones a little bit, but like a normal MRI machine is about 1.5 Tesla. Our innovation was like bring a fundamentally new magnet technology. So in 2021, we built in collaboration with MIT this, we called it the toroidal field model coil. So it's a little bit smaller than our actual magnets on SPARC, but it will reach more than 12 Tesla on the middle. So like as opposed to 5 or 6, more than 12. And it's based on a technology called high temperature superconductors. This was discovered in the 1980s, won a Nobel Prize. But up until maybe 10 years ago, you could only make very, very small quantities of it, and you couldn't like reliably make high volume. So now it's more of a commercial product, so we can turn this into a magnet. This is one type of magnet technology we developed. This is another one, a cable-based and a plate-based type of magnet. And the basic idea is that we're doubling the magnetic field, but in fusion, a lot of things go like field squared or cubed or to the 4th power. So by doubling the field, you have this huge range of benefits in the tokamak, in the type of machine we're building. So basically, like, we've developed this new type of magnet and is now like basically in commercial production. Where do we go next? So like this is not a magnet lecture, so I'm not going to spend too much time talking about magnets. I will mainly talk about fusion. We are now building this tokamak we call SPARC. It's not an acronym. It used to be an acronym. It's like the SAT. It's no longer an acronym. This is a basically demonstration plant. So this you saw the intro overview slide, but like basically this is a facility. It's just outside of Boston. It's designed based on the same physics basis, same physics understanding as the ITER project, which is a large international collaboration in the south of France. But this very, very high magnetic field reduces the size considerably, and I'll talk more about that later. For tokamak aficionados, it is a standard aspect ratio machine, very far from pressure-driven stability limits, has a moderate Greenwald fraction, and is heated with radio waves. The initial operation is aiming to get Q, this ratio of power out divided by power heating power of greater than 1. But the actual machine is designed, its like eventual design limit is Q of 11. So 11 times power out over power in, and a fusion power of about 140 megawatts. It's worth noting doesn't produce electricity. It produces heat. The economics of install the steam stuff on this demonstration plant were very bad, so we are not choosing to do that. Fortunately, people know how to build steam turbines pretty well. We've built, as a civilization, a lot of those, so we're not like particularly worried about like retiring the risk of can we build a steam turbine. This machine is under construction near Boston, so this site here is about like 45-minute drive, hour train ride outside of Boston. And you can actually see a little bit of our headquarters manufacturing facility down here as well. And in my like overly simplified description of why are we building SPARC, it has two goals. One is like do Q greater than 1. Q greater than 1, like scientifically, isn't actually that interesting because you're making more power out than in. But to heat the plasma, only the helium nucleus, the alpha particle, actually self-heats the plasma. It's charged. It stays inside your magnetic field. It collides with the plasma. It heats it up. The neutron is neutral, does not care about your magnetic field. It just shoots straight out. And it takes about 80% of the energy, and that's due to momentum conservation. So only about, even with Q of 1, only about 20%-ish of the heating of the plasma is actually self-heating. And so when people talk about burning plasma, that's actually a Q of 5. And burning means that more heating comes from the plasma heating itself than you get from some kind of externally applied heating source. Again, like, so Q of 1, is it scientifically interesting? Big deal for the world. Like, it is a proof, a proof that this technology works, that you can make net energy. But, so that's why, goal 1, do Q than 1. This proves to the world that this thing works. Goal 2, learn for ARC. And that is where this, like, one of the reasons we're designed to Q of 11 and not Q of 1 is that we can demonstrate actually like burning plasma physics, get much closer to what a power plant will look like. And I'll talk more about like what do we plan on learning in a bit here. And just for, in short, ARC is our power plant. Why is the second goal learn for ARC? This is a great science experiment. We'll learn a lot. It's a great demonstration. CFS is in Fusion to build power plants. The science is super interesting. It's like important for the world. Advancing science in general is important for the world. Like our mission as a company is like make clean electricity, make like clean, firm electricity. And so like primarily SPARC is a stepping stone to the eventual goal, which is a commercial power plant. So a bit about SPARC. I apologize for this like bad table, but this is what we call like the baseball card of a tokamak. So if you like look at tokamaks and you try to compare tokamaks, these are the metric people look at. Targeting operation in 2027. It will look at H mode, which is a way of running plasmas, higher power, heat exhaust inside the machine, and eventually Q of 11. This baseball card, I'll read a little bit of it, but the R is the major radius. That's like the distance from the hole of the donut to the center of the bread of the donut, is 1.85 meters. Minor radius, which is the width of the bread of the donut, is 0.57 meters, 12 Tesla magnetic field on axis, has almost 9 megaamps of plasma current in it. This kappa, which is the elongation, that is the ratio of the height to the width of the plasma of roughly 2. The volume average temperature will be roughly 7 keV. The peak temperature is more than 20. Density of 3 10 to the 20 per cubic meter. And then basically, aiming down here for roughly 140 megawatts of fusion power with a Q, a gain of roughly 11. How do we heat the plasma? Brief side on that. We use radio waves. It's 120 megahertz, basically FM radio. Like FM radio is like, I guess, 89 or 87 through 108 megahertz, just a little bit above that. Basically, if you can shoot a electromagnetic wave in at the same frequency that the particles are orbiting, you can resonate with that orbit and basically continuously transfer energy from the wave to the particle. And so we heat with radio waves that way. And then this ohmic heating, I mentioned before that you're driving an electrical current around the plasma with the transformer. Plasmas are very good conductors. They are not perfect conductors. And if you're driving almost 9 megaamps of current through something, it'll have some heating. So that's how we end up heating the machine. I'll also say I have a picture of SPARC here, a rendering. These are the toroidal field coils, these D-shaped things. The central solenoid, this thing in the center. These other magnets are the poloidal field coils. You might mention that looks like a lot more things than you mentioned in your cartoon of a tokamak. That is true. Unfortunately, tokamaks have lots of other parts, but they very, very rapidly devolve into like the engineering details of building one of these machines. Early tokamaks, like the T3 tokamak, didn't have that many parts. We've just invented a lot of complexity over time. This thing is under construction. So 3 years ago, this was a field. basically nothing. The area of Devens we're in actually was previously a military base, Fort Devens. There's still some base left, but it was largely decommissioned 20 years ago. This area actually used to be military housing, but 3 years ago this was a field. I'll talk a little bit about this, but basically the Tokamak will be in the center here in this big concrete box. At the front here, we have a building for basically scientific instrumentation. We call it diagnostics. Building on the right is for the radio frequency heating system. In the back is for power supplies to power the magnets. And on the left here is heat extraction. So cryogenics to keep the magnet cold at roughly 15 Kelvin, and then warm helium to take the fusion heat out at room temperature or a little bit higher. Big tank farm. We have a lot of helium for coolant, a lot of nitrogen for coolant. So these are all the cryogenics in the back. This is the industrial parts of the facility. So you can see helium compressors, the cold box for the helium to get down to 15 Kelvin, and then a distribution box to kind of send it to all the magnets where it needs to go. We started assembling the machine. So this is earlier this year. This is the base of the cryostat. So cryostat's a large vacuum chamber. It's the bottom of the machine. It basically pulls a large vacuum so that you can keep the magnets cold and keep the vacuum vessel, the fusion part, hot. Started assembling that now. This is the actual vacuum vessel itself. So I didn't talk about it too much, but in order to make the plasma, you need to first suck out all the air. You want only hydrogen in there. You don't want nitrogen and carbon and stuff. So there's two halves of it. It's a little bit hard to see here, but this is one half. The other half is over here. You'll have these two semicircles that you kind of bring together and weld in the center. So that's being manufactured right now. And then we produce our own magnets. So as I said before, the key new technology in this whole endeavor is magnets. We have about 100,000 square foot manufacturing facility. 5 years ago, when we were making the first of these, it was like a person by hand taking the superconductor and putting it in a thing. And now we've got a full scale manufacturing facility. So just on some numbers briefly, this D-shaped thing here is one layer of one of these magnets. There's 18 D-shaped toroidal field coils. There are 16 pancakes in each coil, so there's 288 total pancakes. We now make about one a day. It's every day, including today, we make one pancake, rolls off the end of the assembly line. That is in comparison to the first one, took a month between the first one and the second one. So we've gotten a little bit faster, which is good. And so this is our kind of production rate for SPARC, and we're almost 90% done with production of pancakes. So we're pretty far. These are also called pancakes. We're pretty far along in the production of this aspect of the magnet. So it's basically a very long groove, a very spiraled groove where you insert tape into around this plate. We also have the other type of magnets. This is a poloidal field coil. You can see the insulated cables. They go around this way. We're installing some instrumentation on them in this picture. So we're also far along in that production. We test every magnet. So this is a cryostat test stand where you put one D-shaped magnet in the center here. This is a full-scale one for SPARC. Cool it down to 20 Kelvin, test it up to full current. You cannot test it to full magnetic field because you need all 18 coils around it to make the full field. So at full field, it'll be about 20 Tesla on coil, a little bit over that, and 12 Tesla in the middle of the machine. With only one magnet, you can only get up to about 12 Tesla total on the coil. So it's full current, not full field. And again, for a sense of scale, people around it here. So we'll test every coil. As I said before, this machine, the goal is to do Q to the 1, but we also need to do science on this machine. I'm not going to pretend that there's no science questions open. It's a collaborative team. We will publish these results. Again, we think that the fastest way to get to fusion is to be open about the science of it and to really quickly investigate basically the key open questions for the ARC power plant. So I'll go into a bit more about ARC later, but there's two general categories of learning we think we'll have on SPARC. I've broken this down to confirmatory things, where it's we think we have a pretty good answer. We have a pretty confident in our projections, but we need to actually do the thing. We need to actually measure it. So my examples here are confinement scaling. So when I say SPARC is going to make 140 megawatts, how do I know that? It's a combination of a large empirical database of other tokamak plasmas and first principles modeling of the turbulence in the plasma with a type of theory called gyrokinetic theory. Those actually agree pretty well, within 10 or 20%, which for physics is pretty good. For engineering, you might want better precision than that. And so SPARC will have to like prove out those scalings, those predictions. Radio frequency heating, again, we know this works on current machines, but we want to do it on a higher temperature one. These burning plasma effects, again, we have a pretty good theory for how that should affect the plasma. We want to actually do it. There's some exploratory things. So there's areas of tokamak physics where we know there are challenges and we have good ideas to all the solutions, but we don't have the solution in hand yet. And I'll give the specific example of heat exhaust. So this plasma, this is SPARC on the left here, makes 140 megawatts of fusion power. 20% of that comes out in the plasma itself. So the neutrons shoot straight out. That comes out volumetrically. It's actually easier to remove the heat that way. The rest of it comes out in a very, very thin layer, a thin ring around the machine. That's due to the magnetic geometry of the machine. And it turns out that spreading that heat out, you need to spread it out to remove it, because sustainably, reliably, can be challenging. There's a lot of machines that have done this at various ways, various power levels, and we just need to do it at a very much higher power level than previous machines. So we have a lot of great theory there, a lot of great simulations. We need to explore a little bit to find exactly the right solution for the power plant. And so I'll talk more about ARC later, but there's still some physics learnings on the pathway from SPARC, this demonstration machine, to ARC, the power plant. We'll validate a lot of these predictions. So I mentioned before these predictions. Basically, what I'm showing here is this is a radial profile. So this is the middle of the plasma to the edge of the plasma. This is temperature, electron temperature in kilo electron volts. It's worth noting that in plasmas that are this hot, the electrons and ions move past each other enough that they don't necessarily have the same temperature. They can have multiple temperatures in these two kind of coexisting fluids. So ions tend to be a little bit cooler. So here's the ion temperature. This is the density. And basically all these different lines are different models, like different ways of doing the prediction. You can see that they all like generally agree roughly. There's some exception, a little bit of exception here and there. But these, like in general, these theories agree quite well in these like large computational codes. Actually, part of my PhD thesis before CFS was validation of gyrokinetic simulation codes with turbulence measurements in tokamaks. 10 years ago, these codes were not good enough to design power plants with. Over the last 10 years, they've gotten a lot better. Both the theory itself has improved significantly and our ability to compute it on large supercomputers has gotten a lot better. So SPARC will validate this. We have these predictions. They vary in the Q gain prediction from a little over 6 to something like 11, depending on exactly which model you use. So we'll have some ability to refine those projections going forward. We'll also look at the impact of something called a disruption. So a disruption is when you have a unanticipated, unintentional movement of the plasma somewhere, or a loss of the plasma confinement. This will basically, very, very rapidly, the current goes away and the thermal energy of the plasma gets deposited somewhere around the edge of the machine. People are worried, like, is this going to melt a hole in the machine? No. The shortest version of that is that, like, the same reason as like a neon light. Temperature, really high. Density, really low. And so the total stored thermal energy in the fuel is very, very, very little. So just an example, in like SPARC, there is 1 gram of fuel total in the entire machine. So it's very, very little power. But these disruption events can cause very, very small melt events. So you have a tungsten layer facing the plasma. You could melt very small portions of that. It's not the end of the world, but like you don't want to do that regularly. Otherwise, you don't have a very like long-lived power plant. There's actually another effect called the runaway electrons, where if you start to have a disruption, you lose some of the thermal energy, but you still have a lot of plasma current moving around. You can concentrate all that plasma current in a very small number of relativistic electrons. And we are basically testing this like weird non-axisymmetric coil that intentionally scatters all these electrons all over the place to spread out the energy. So all of these are basically ways of spreading out the energy inside the machine during a disruption event. I talked about heat exhaust, so I won't go too much into this, but basically SPARC has this like weird looking leg in the bottom of the machine. These red lines are basically the edge of the plasma. You can like put that edge in all kinds of weird locations. You can also do some like funky stuff where you have these complex magnetic geometries. All of this is saying that like we will look at different ways of exhausting the heat outside the edge of the plasma. And so that gets us to the next step. So as I said before, SPARC will be a huge scientific a huge deal scientifically. We'll learn a lot from it. But the goal of this is to go to a commercial power plant. And so I'll talk about now a little bit about ARC. ARC is also not an acronym. It also used to be an acronym, but it is our power plant concept. In terms of timelines, we are intentionally vague when we say early 2030s. We, as much as possible, would like to have a firm sense of the date before we commit to something. So we're saying early 2030s. So yeah, commercial fusion power plant. It's aiming to be 400 megawatts net electric. So for those who don't every day look at power plant sizes, this is like a medium-sized natural gas plant. It would be a very small nuclear fission power plant or like a smallish coal power plant. So it's power plant size. It's not massive. It's not tiny. And this is roughly what it looks like. So I won't talk through too much, but I'll show a comparison later. It's a little bit bigger. Still has this plasma bit in the middle. Still has toroidal field coils. The main new parts are the pieces to get the energy out. You need to take all this heat out and eventually turn it to electricity. And my last, bullet, which is always controversial, is like one power plant is great. To really make a difference, you need to build lots of them. So like CFS as a company, our goal is to prove out fusion, build a power plant, but really like to actually make an impact on the world energy market, you need to build like thousands of power plants all around the world. So like we, at some point in the future, need to look like a heavy industry manufacturing company. We need to like manufacture these, install these, really do infrastructure, which is going to be an important part of like really developing and deploying new energy. So what is ARC? Here's my a little bit like I won't go all the numbers here, but like in comparison to existing tokamaks. All the way on the left here, this is ASIC's upgrade. That's the one I worked on in Germany. This is SPARC. This is the Joint European Torus in the UK. This is JT60SA in Japan. That one just came online 2 years ago, I think. This is ARC, for context. It's a little bit bigger than JT60SA, not that much bigger. And this is ITER. So this is the large international collaboration in the south of France. I'll say it primarily as a scientific mission. Like it's we can think of it like the Large Hadron Collider a little bit in terms of having a scientific mission, but it has one generation older magnets, and in terms of the gain Q, it has basically a similar goal to SPARC. So you can fit probably a SPARC inside of ITER or multiple of them. So just to give you a sense of like how big of a deal this new magnet technology is, and all of this is to say that like. ARC is large, but it's not outside the size of like what people have already built for tokamaks. But again, much higher magnetic field, much better confinement, a lot more of those little orbits inside the plasma. And so we think, or all of our predictions say that it should be very viable as a commercial power plant. Okay, a little bit about heat in and out. So I'll talk now about, like I said, the biggest new parts on ARC are getting the heat out. So zoom in like a little bit. How does the plasma come out? Here I'm drawing this little black line is let's say the vacuum vessel, so that edge of the vacuum chamber that holds the plasma. Orange blob plasma. This blue stuff here on the bottom is my cartoon for the plasma facing material. We use tungsten. There are other materials you could use. And then the little purple line here is the edge of the plasma. So heat goes in with radio waves. Fusion happens. All the neutrons just shoot straight out. They just leave because they're not magnetically, they're not electrically charged, so they don't move around your magnetic field. The other 20% plus the radio wave heat that you put in will leak out via turbulence. So this is like you can think of it like convection, just like the conduction or convection. The plasma, the heat just like kind of leaks out the edge. That is eventually concentrated down into the bottom due to the magnetic geometry. So I won't talk too much about that, but the power will come out that way. In a power plant, you want to capture all that energy. So people like often think about like neutrons. Oh, those neutrons are bad. They just activate stuff. No. We want neutrons because like that's where all the energy comes from. Like that is the revenue. That's the electricity that we are putting on the grid. We need the neutrons. But you can't just like let them go anywhere. You have to collect that energy somewhere intentional so that you can use it to make electricity. So here's again my cartoon. Here's a toroidal field coil. Here's the central solenoid. Here are some polydal field coils. Here's the fusion happening in the plasma. You surround it with some kind of material to absorb those neutrons. There's a bunch of ways you can do this. We have chosen a molten salt called FLIBE. It is a fluorine, lithium, beryllium salt. Typically, you want something that has lithium in it. So I haven't talked too much about like where do you get the tritium from, but I'll briefly on that. Deuterium naturally exists. You can filter it out of seawater. Roughly 1 in every 6,000 hydrogen atoms on Earth is deuterium. Tritium does not occur naturally, so you have to make it. But if you hit lithium with a neutron, it will create tritium. So basically, our plan to produce the tritium is produce it yourself inside the tokamak and use that to fuel the tokamak. This molten salt also then gets hot because you've just put a bunch of heat into it. You then pull that out. You get the hot salt out. You heat exchange that with water. You make steam. You spin a turbine, and you connect that to the grid. So I'll say a little bit ironically, we're doing all this like crazy technology development to build this magnetic chamber in 100 million degrees and da-da-da-da. And it's like the best way to make electricity is still to boil things and put it through a turbine. Turns out works really well, and that is the strategy. Future looking, there are other ways to do this, totally fair. We will look at that in the future. Largely our strategy to date has been like, this part is really hard. So like do the hard part and like don't unnecessarily make other parts harder. So like choose a super well commercially proven technology of like I can like call a steam turbine manufacturer and be like, I'd like part number 3 from your catalog. And like we ourselves will focus on this like totally new challenging part, which is the fusion part. So all to say, that looks very, very standard. There are other things you can use for this molten salt blanket, or for a blanket in general. Typically, it has to have lithium. You can use liquid lithium, like metallic lithium, lead lithium. You can use lithium ceramics that then you cool with something else, like helium. Bunch of options, all somewhat challenging in different ways. We think this molten salt solution is the best overall solution, although it is certainly going to be a challenge. This is not just like some theory cartoons we're drawing. We do have like very concrete plans to build this facility. It's actually not too far from here. It's a couple hours. We will build the ARC power plant. It's actually already on Google Maps in Chesterfield County, Virginia. So this is a Google Maps picture. We announced that site roughly 6 months ago. Right now it's still a field, but we do not too far in the future, we'll start actually doing development on that site. We have very strong partners, both state and locally. We wanted a site that wanted us, so we like talked to the community. They're like, fusion, yeah, sounds cool. Like, let's do it here. We also have like very strong partnership with the local utility, Dominion, who will like basically, put that electricity onto the grid. And we're very late stage discussions with offtake agreement partners, like the person who's going to buy the electricity. Also, Virginia needs a lot of electricity, so they're very happy to have more power plants come there. And we're moving fairly far along in the engineering design of this facility. You might look at this and be like, well, that looks kind of like that other thing you're building, which is exactly the point. So this is a slightly larger version of SPARC facility layout, but again, Tokamak here, a whole building dedicated to maintenance, which would be challenging. Some of the measurements and tritium in the front, a lot of the standard industrial equipment in the back here. On the left, this is this molten salt piece to take the heat out. This is a turbine hall with a very boring but very effective steam water turbine in there. Switchyard in the back, and these are dry cooling towers, so not evaporative towers. A little bit less efficient, but means you don't need water, nearly as much water intake to the plant. More plasma happening. And so that's a bit of that's like an overview. And so like as a company, our goal is build on known science. Advancing science is very important. That is not our mission as a company. Our mission is to make electricity. Build on known science, combine it with new technology, bring it together in SPARC, learn exactly what we need to get to a power plant, and go build that power plant. So high-level view, that's what the power plant is. A little bit on like the road ahead. Like where are the challenges? Where are the opportunities? Fusion is hard. I agree with that. No one's saying this is easy, but we are saying it's worth trying. Part of the job, honestly, which this isn't very sciencey, but is like SPARC needs to continue to happen. Like this is a large, first of a kind, complex engineering project, and like every day you need to do a thing. It's like I mentioned earlier, like we make one pancake a day. If we did not make one pancake today, like we did not do our job today. So like we need every day, you just need to continue to execute this project. Again, not the most scientifically exciting thing, but just like super important for like building big stuff. As I said before, we need to do some science and technology. So learn some stuff on SPARC. On ARC, we'll continue to do some R&D in parallel. So produce and test materials that will withstand the thermal and radiation conditions in ARC. Develop and test at scale FLIBE molten salt components. So people have done a lot of FLIBE stuff at kind of lab scale or maybe a little bit bigger. We need to make like industrial sized pumps, industrial sized pipes that have industrial sized heat exchangers attached to them. So there's a lot of like industrial scale up that needs to happen on this FLIBE technology. As well as some tritium science and technology understanding for ARC scale. So like a very large throughput of this tritium material separating out of the FLIBE, that kind of thing. In parallel to the R&D and building SPARC, we're continuing to design ARC. This is another engineering product. We're still in the fairly early stages of the design. As you can see, like most of the stuff we have now is like not super detailed. It's similar to where SPARC was in maybe 2019, 2020, early on in the stage of that machine. So we call it the pre-conceptual design phase, and things evolve rapidly. So the team comes together, design, does a bunch of analysis for like, these things need to change, come together, a new design for ARC, make these changes. So it's a very rapid, quickly changing thing. And you might also say, like, wait a second, how can you design this next one when you haven't even finished building the first one? Great question. A lot of the plant you can design without knowing the exact detail of what this shape of the diverter leg looks like to get your heat out. You can design like the pump for the molten salt system. You can design some of the tritium stuff. So the goal in this early design is to like be as flexible as possible in the areas where we know we have the largest uncertainty, so we can include late design input from SPARC. And this is less in the technology, but maybe also an important piece of this. I mentioned earlier that the goal is not to build one of these, one awesome. We need to build thousands to have a real impact. And like part of this is like the ecosystem. So like we need to build an ecosystem in the world that is ready to do fusion. Like when the technology is ready, which is not quite there yet, but it's close. When the technology is ready, we need a world that is ready to accept and rapidly deploy fusion. So this means regulation. Very, fitting being here in DC. The UK and the US have both decided to regulate fusion like a particle accelerator. The US, this was ruled by the NRC in 2023 and then passed into law by Congress in 2024. So it's regulated like a particle accelerator, very, very separate from fission. It's a risk-appropriate framework, different risks, different regulation. We also are hoping that other countries will follow a similar framework where you don't have to like completely design a different power plant in every country because there's different regulation. In addition to that, we need to develop a supply chain. So we are already actively doing this. We have an active supply chain team at the company. Just this superconducting material over the last 5 years has scaled up a massive amount. Like when we said we were originally going to do this, 5-ish years ago, people were like, you can get all this tokamak stuff, fine. You will never buy enough superconductor to do that. And it's like, it was hard. You had to like work very closely with suppliers around the world to help them scale up. But like they saw us, they're like, there's a customer. There's a real customer who's going to buy this stuff. Like we will scale up. So part of that supply chain development. And I think one of the common things we get, especially within the fusion industry, is that like, each one of these machines is so hard. How will you ever build that many of them? It will not be easy, but to build all of the superconductor, all of the HTS you need for 1,000 ARC plants in a year, you'd need like 5 first solar thin film factories. It's a lot of factories. It's not that many factories. You need to make pancakes, those layers of the magnet, in one Tesla Model 3 factory. And you need to make the cases, the steel of the magnet, in one Hyundai Heavy Industries shipyard. So like all of this is to say that like the technology is hard. And on top of that, scaling it up will be hard. But when you go talk to like heavy industry, like people who build stuff and build it at scale, they're like, yeah, you could scale that up. Like if you can figure out this like fusion thing and like you can actually make this work, we can build a lot of it. And so I think, for myself personally as well, coming from an academic background, coming from the physics background and going into industry, like this part seemed like impossible. There's no way we can do that. And you would talk to people who do this and they're like, yeah, we'll figure that out. It will be challenging. We can figure it out. But again, this comes back to one power plant's cool, 10,000 power plants changes the world. And it comes back broadly to our pathway to a fusion future. So I will say that's a bit about me. It's a bit about fusion. So fusion, basic process, powers the universe. hopefully, potentially a huge game changer in the energy industry. We are working on a type of machine called Tokamak. People built a lot of these. We are combining that with a new magnet technology based on high-temperature superconductors. We're now building the SPARC tokamak just outside of Boston. And we are getting ready for the ARC fusion power plant in the Richmond, Virginia area in the early 2030s. So thank you very much, and I'm more than happy to take questions.
Okay, we have time for some questions. We'll start with the blue microphone.
Thanks for the talk. I'm Fred Wise, not a member. So you talked about the projects going on in other countries like Japan and France, and I was wondering, like the technology and the regulatory framework, is the U.S. the place that you see this going commercial first, or is there somewhere else in the world that is more ahead of it or welcoming of that industry?
Yeah, it's a great question. So, I mean, I will say we chose the U.S. for our first power plant, partly because the regulation was figured out. If regulation hadn't been passed in the U.S., like it's really hard to go build a commercial product somewhere where you don't even know what the rules are. So like that's a super important part of this. And like the UK, so the UK actually was first. The U.S. quickly followed. That gave regulatory certainty with a risk-appropriate framework. So that's like a very important piece of doing all this. In terms of like the ability to build stuff out, there are a bunch of private companies in fusion around the world. More than 25 are in the U.S. out of a total of like 40 something. So like the majority are in the U.S. The U.S. has a good, good talent base for this. The venture capital ecosystem means you can get financing to do it. So there's a lot of good work happening here. There's other countries working on it. The UK has a very, very strong fusion program. They're moving very quickly, also on the regulatory side. China is increasingly investing in fusion. Regulations a bit different there, as well as the idea of a private company. But they've been moving very quickly. Other countries as well. I'm at CFS because I think we've got the best shot of doing this first. But it's a good thing for the world that a bunch of people are working on this, and there's both multiple companies, but also multiple countries investing in it.
Red microphone.
Thanks, Alex. That was an excellent talk. I just want to know what is the high temperature superconductor thin film? Is it magnesium diboride? How do you make the thin film?
Yeah, great question. So we don't make it ourselves. We work with vendors to make it. It's yttrium barium copper oxide, so it's a ceramic YBCO ceramic. The form that we purchase it in is a tape, like a ribbon almost. It's mostly it's about 100 microns thick. About 50 of that's hastelloy, a type of steel. There's some buffer layers for deposition. The actual superconductor, the YBCO, is about 1 or 2 microns thick. So it's a ceramic, but it's flexible, and that's coated in copper for the rest of the rest of the thickness of the tape. So thin film deposition is like the primary process you use to make it. We have multiple vendors around the world that we purchase it from. And so we have enough now for SPARC, and we need to scale up again for ARC, and then scale up again for multiple ARCs. But yeah, YBCO primarily.
Could you just say a little bit about the materials that they're using and where they're sourcing them from?
For the superconductor, yeah. So
the YTTO.
Yeah, YBCO. So maybe on the materials side, briefly, it's like the cost of the superconductor is completely dominated by production cost. There is a finite cost of like the material itself, but that's like a couple % of the total cost. It is like dominantly making it is hard, making the material. Where do our suppliers get the material from? Like I actually don't know all of our suppliers, but steels from around the world, copper is not particularly hard to come by. The yttrium is a rare earth, but you need very, 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 very little of it. Like fractions of a % of the tape is actually yttrium. I don't want to quote the exact number, but like you need very, very little actual of the rare earth.
Blue microphone.
Hi. Elliot, not a member, very strongly interested though.
Great.
So I've actually followed a couple of other commercial fusion companies, in particular General Fusion and Helion. I'm a big fan of both of them. I know both of their methods have implicit thermal conversion in that I think Helion's does direct energy capture with, I believe, magnetic induction, and General Fusion using liquid metal also, like the confinement of the liquid metal directly aids in the heating.
Yeah.
Given that your fusion technology is not necessarily like aiding into like the heat conversion, Where's the confidence in terms of this type of technology? Is it just because tokamaks are just so extensively studied and like well known and like all the science behind it?
Yeah, it's a great question. So yeah, like I said, there's a bunch of fusion companies. We know General Fusion well. They're based just outside Vancouver. Helion as well. They're based Washington State, broader Seattle area. Great. Other people are trying stuff. It's really good to have many options on the way to a power plant. The reason we chose tokamaks is there are potentially advantages of other geometries. So this pulsing with the induction into the magnets that Helion could do could potentially be a more efficient way to produce electricity than the steam stuff. The general fusion piece as well, it's like their liquid metal compression thing, again, potentially a more efficient way of producing electricity. We chose a tokamak because the physics of the plasma tokamak part is the best understood, and we think you don't need to go discover entirely new physics to get to a power plant. There's a bunch of other concepts, Helion, general fusion, a bunch of other things where it's if they work, it could be great. But we think that at least in our view, the probability of them working, or more, maybe a longer way of saying it is the amount of additional physics work that needs to happen is greater. And at some level, we think it is easier to schedule engineering than it is to schedule physics. And we've chosen to take engineering risk instead of physics risk. But that's not to say that we're happy other people are trying other things. Maybe that's the overall answer.
Red microphone.
Ciprian Ivanov, member. What about the regulatory environment is so compelling? Why is it enticing that you're regulated like a particle collider?
Yeah, it's a great question. So in the US and a lot of countries, fission is heavily regulated, and there's good reasons for that. There are safety concerns, there are proliferation concerns. There's history of radiation releases in fission plants. Because of that, the design itself is incredibly tightly regulated, primarily around risks of meltdown. That dominates how fission is regulated. Because of that, though, there's a large amount of incredibly strict quality standards on stuff because the risk, the consequence of a failure is large. There are incredibly strict requirements on how the actual design of the plant itself is regulated, not just how you handle it, to the point where the process can take many, many, many years to get a license, and you need a license just to even start construction. You can't even start moving the dirt necessarily until you have at least some portion of the license, and it costs a lot of money. So it's fission. One of its challenges, I'll say, we should build more fission. There's a lot of advantages to it. One of the challenges it has, at least in the US, is that it's typically very slow, and some aspect of that is all the requirements around the regulation. Fusion, the risk profile of what could go wrong and the consequences of that are fundamentally different. You don't have this meltdown event. You don't have long-lived transuranic material, and so how do you need to build it? How do you need to contain it? You have containment. You don't have that for fusion. Are a fundamentally different process, and so it means you can apply different quality standards that are more appropriate to the risks. You don't have to get these licenses to even start construction. Even actually, SPARC is regulated by the state of Massachusetts, not directly by the federal government. And actually, ARC in Virginia will be regulated by the state of Virginia, the Commonwealth of Virginia, not the federal government, because the risk profile is different. So the regulation is important for speed, and we think it is should be regulated appropriate to the risks of the technology. Hopefully that answers the question mostly.
We're going to take a couple of questions from the web, and then we'll go to blue. Then we'll go to red. Web, blue, red. Web.
Thank you for your talk. Our first question comes from Dave Rabinowitz from Oregon, who is a member. What is the projected lifetime for a reactor, given that high-energy neutrons are not kind to materials?
Yeah, great question. So we're still developing the exact requirements around this, but the full power years, so the operating time, the time when the plant is on, something like 20 years for the first version. This is a design choice. And it's at some level you could choose to make it longer, but we know on these first couple we're going to learn a lot, and we probably want to make the second couple better. Something like 20 years. Question about neutron changes, neutron damaged materials, totally valid. The piece closest to the plasma, that vacuum vessel, on ARC will be replaced roughly every 1 to 2 years. That's like the main consumable of the plant, is that vacuum vessel. So you actually split the tokamak in half, take out the two halves of the vacuum vessel, put in a new vacuum vessel, and put it back together. And that's roughly every 1 to 2 years. And actually, in terms of like operating, that looks kind of like a fission power plant refueling. It's like most fission power plants, approximately every 18 months go down, they refuel, they come back up, and they continue operating. So the lifetime of the most consumable part, 1 to 2 years. Lifetime of the plant, more than 20. Good question, though.
Another question from the web.
Yep, one more. Thank you. Michael Haken from Silver Spring, Maryland, who is a member, asks, how much energy will it take to fire up SPARC, and ARC reactors to achieve unity gain? And then how much is required to reach the projected 400 megawatts on the ARC, output for the ARC?
Yep. So how much power do you take to start the machine? There's two, for SPARC, I'll start with SPARC. There's two pieces of that answer. The first piece is like once you've made the plasma and it's just operating, how much power do you put in to keep it hot? So it's about a little over 12 megawatts to keep the plasma hot when it generates 140 megawatts of fusion power. That's primarily radio waves. To start the plasma, mainly what you need to do is turn the magnets on. Like the majority of the energy to start the plasma goes into turning on the magnets. And actually what you're doing there is primarily just storing energy as magnetic field, like is it energy storage. So for the 10 seconds when you're turning on SPARC, it takes more than 100 megawatts of power to turn the machine on. But when you turn the machine off a little bit later, you actually get most of that back because you stored it as magnetic energy and then you take the magnetic energy back out. And you would store that locally on the site. You don't pull it directly from the grid. So either batteries or a motor, mechanical spinning motor generator or something like that. And you kind of like spin this up over a long period of time, put that energy to the magnets. When you're done, take it back out of the magnets, store it again. So it's not like lost. But you do need a bunch of power for a short period of time to like turn the machine on. In ARC, the on-off cycle is a bit different, but like how much power do you need to like keep the plant running? 400 megawatts electric. The total thermal power is actually a little bit over 1,100 megawatts. To make that happen, you have a gain of roughly 50, so your heating power is about like 22, 23 megawatts of heating power to keep the plasma fusing in ARC.
Cool. Thank you.
Just curious, you didn't say anything about how you get the radio wave energy in there and what kind of effects it has on the plasma and how uniform it has to be and anything like that.
Sure. So we generate the radio waves. The traditional technology for previous tokamaks was like vacuum tubes, the kind of old school computers. Power electronics have come far enough in the last, let's say, 10 years that you make this totally solid state now. So solid state power boards, plug them in, big cylinders, combine them together. You transmit them through a big pipe that is a huge coax cable, a coax pipe basically. So like the thing you plug into your like internet router is a coax cable. This is a much, much larger, higher power version of that. Those go into antenna structures. So you typically have a conducting antenna structure that's like a strap. You typically have multiple next to each other. That basically launches, it's in like the antenna on a car or whatever, or I guess on a radio station. It launches the waves into the plasma, and then they propagate through the plasma. There is some challenges around there's a cutoff layer, which would reflect the waves at a very, very low density of the plasma, so you need like the plasma pretty close to the antenna. So the antenna and the plasma are a couple centimeters apart. You launch the waves out the antenna, they go through an evanescent layer into the plasma, and they get absorbed in the plasma.
Blue microphone.
Remember, as you mentioned, the density of the plasma is extremely low, like a gram in several cubic meters,
Yep.
right? What limits that density? Why couldn't it be a few times bigger? And the second question is, do you have to keep the tritium density in there constant? You're feeding it tritium all the time to keep it constant. How does that go?
Yeah, so I'll do the second one first. It's easier than you would think. It sounds really hard to get all the fuel in, and there are complicated ways to do it if you want to do something fancy. You can like freeze pellets of tritium and then shoot them in. The simplest way, which mostly works, is you like puff a little bit of gas into the edge of the machine, and it just kind of like sucks itself up. It gets actually pinched up into the plasma as it ionizes. So on like Alpha CMOD, the only way we fueled it was like you have this vacuum chamber, you puff a little bit of gas. The gas just, again, it's neutral, doesn't care about your magnetic field. It moves around. Once it hits the plasma, it starts to get hotter and ionizes, and that gets actually pinched into the plasma. So that part is most parts of fusion, really hard. Get fuel in, less hard than you would think. The other part of the question was, yes, continuing to fuel it. A limit to density, sorry. Yes, you're right. Different types of fusion machines have different density limits, pretty wildly. Laser fusion can do very, very high density because they're compressing this little pellet. In a tokamak, there is something called the Greenwald density. It is named after a guy named Martin Greenwald, who's at MIT. And it is a edge turbulent instability that if you have too much density with a ratio of the size of the plasma and the amount of plasma current, so basically the plasma current density, you have an instability near the edge of the plasma, which typically leads to like a big disruption. And so that one is an example where like empirically we understand it very well. The empirical formula for it's actually pretty simple. First principles, we have like a general idea of why it happens, but we don't have like a really good first principles description of why the Greenwald density is a thing. But yeah, in a tokamak, you're limited to this thing called the Greenwald density.
Red microphone.
My name is Frederica Derima. I'm a member. Thank you for your presentation.
Of course.
I have a question that was asked before, how much energy you put in versus what you get out, and the question that Mike asked. And you answered it in a certain way, but you didn't, and you talked about instabilities, but what you really want to have is control of these instabilities. So it's not a kind of a static system. You want to have a continuous control.
Yeah.
How would you do that? And also you showed a bunch of designs for the magnets. It was about 10 kind of configurations. Have you done modeling to pare down that? And how, given a design, how then you will apply control?
Yeah, control in general is a great question. Largely, the control of a tokamak boils down to like a couple things. The biggest one is the magnetic fields. So like you have these polyidal field coils to control the radial position size of the plasma. You have other magnets actually which control the vertical position and the shape. So like most of the control is the magnetic geometry, the magnetic forces you apply with the magnets. If there are a number of like known stability limits. Greenwald density is one of them. There's something called the kink instability, which is you can't have too much plasma current compared to your toroidal field. There's ballooning limits. There's all these known instability limits. The majority of those, if you know what they are, don't go near them. It's like a case of like, don't put too much fuel in, or like, don't try to make your plasma current too high. There are some things that like are a little bit harder to predict, but like the majority of things that cause instabilities are like known limits that you just stay away from effectively, which limits a little bit how much performance you can get out of a machine. Like if you could just ignore those limits, yeah, it'd be great. You can go to much higher density, much higher current, great. But we know what the limits are, so you largely stay away from them. And the control is like, magnetic geometry, density, so like fueling, that's another aspect of that's another actuator. And then plasma heating is typically your third actuator. There are other, let's say, more intricate ways of controlling the plasma. We've largely chosen to do the simpler ones. And not have these like very complex waves that you can drive plasma current, or like very fine control of like internal magnetic geometry or things like that. But so it's a real-time control system, measurements of the plasma with diagnostics, controller loop back into the actuators to control the plasma.
Do you have any modeling that you're doing for modeling this kind of processes to figure out and know that you might have a handle how to deal with them?
Yep. Yeah. So today, especially today with like modern computing and stuff, we have a deterministically real-time model of the plasma that we call Comet. It runs exactly 1-to-1 in what time the plasma would run in. We have a control system that we call Neutrino. We run Comet in one computer and Neutrino in another computer, and those talk to each other, basically like to simulate the ability of our control. They simulate our ability to control the plasma with a fake plasma. The term of the day would be a digital twin, although like that can mean like 10 different things depending on who you talk to. So we model it to develop our control systems before we operate it. Before this, people would build the thing and like guess and check, which like typically worked pretty well. But we think we can go much faster by modeling the plasma, modeling the system and modeling the controller and testing them against each other.
Going to take a couple more from the web, and then we'll go to the blue, and then we'll go to the red.
So we have a question from Eric in Sweden, who is not a member. FLIBE is a popular component with liquid thorium reactor projects. How is that choice helping you with the reactor's mechanics, pumps, and other components?
Yeah. So FLIBE is used in a couple other technologies. There's another fusion company called Exemer that wants to use FLIBE. There's some fission companies like Kairos that want to use FLIBE as their component. It's good. It means that there's multiple people that are interested in it. We've learned some stuff from people that have developed FLIBE technologies for fission. It's not in widespread use, so like there's still some development efforts to do. But the fact that there are other groups interested in the same technology is great because it means we can benefit from it.
Perfect. And we have a question from Mario, who asks, how do tokamak reactors compare to laser fusion reactors?
Yeah, great question. They're fundamentally different technologies. My analogy is that like a tokamak is like a coal furnace. It continually burns, it continually fuses, you put more fuel in. A laser thing is called inertial fusion. Basically, it's inherently pulsed. It's like an internal combustion engine. You put a little bit of fuel, you compress it, it fuses, expands, you put some more fuel in, you compress it, it fuses, it expands, like a piston almost. It's lasers. They're pretty different technologies. They make plasma as fusion happens. The technology that goes into making it and the technology to extract the power is quite different. So they're, same plasma physics, very, very, very different apparatus to like make the thing. And people are working on both.
Blue microphone.
Yes, this is Brooke Leque. I'm not a member. Question is the superconductor that you use, the YBCO. I've worked on it a little bit, and as you temperature cycle it, you heat it and cool it, the transition temperature degraded. So do you see that happening in your coils?
Yeah, it's a good question. Most of the degradation we think is from like mechanical strain, basically. It's like not purely the temperature tip. We think it's mostly strain caused by the changing temperature back and forth. We've done like thousands of cycles on some pieces of it. Often there's like, at least in our testing, there's an initial degradation that kind of like levels off pretty quickly, where it doesn't continue to degrade by more cycles until you get to like a huge number. And that's part of our design cycle is that we don't design to the perfect pristine time the first time you turn it on. We've designed to the like where it starts to level off.
You
up
take
to a
into
couple thousand
account the
cycles.
possible degradation then.
Yeah.
Okay.
So
second question is, energy is needed everywhere, even in the developing nations.
Yep.
Where there's significant degradation in the environment.
Mm-hmm.
You say you plan on building 1,000 of these, or 10,000, whatever it was. How much is it going to cost?
Yeah, it's a great question. So the whole thesis of CFS is that like fusion has to be economical for it to like be widely adopted. It's like the reason we are doing this high temperature stuff rather than low temperature stuff is because you can make a much smaller, more affordable plant. Not just because we like HTS, like it's fun. And that like, you know, one of our like central tenets as a company is like, in order for a new energy technology to be widely adopted, it needs to be adopted by the market. Basically, we assume there's going to be a market looking for energy sources. You know, we don't. I don't want to say a specific number for the cost, just because we haven't finished designing the plant yet, so we need to finish designing it. But like largely, our projections show that it should be like of similar cost to solar plus battery, or wind plus battery, or like basically any kind of thing that looks firm. Like a straight up solar panel that like turns on and off sometimes will typically be cheaper, especially with like the learning curves they've come down. But solar plus enough battery to actually be a firm source would be similar cost to fusion. It'd also be like heavily geography dependent. Like in some areas, solar's gonna be great. In some areas, wind's gonna be great. In some areas, especially like really dense urban centers, you don't have enough space to do all of that, or you need huge transmission lines, or you need huge batteries. And so we think fusion's like a much more economical source there. So yeah, we think it should be affordable, and like to the extent that you should be able to deploy it in parts of the developing world, anywhere in the world. Last piece I'll say on that is like, at some level, fusion looks like a manufactured energy. Like a fusion plant, an ARC, in a year uses 100 kilograms of fuel. That is like nothing. Like you can put that in a pickup truck for a year. of power generation. So fusion at some level means you can like build a plant somewhere, deliver all of the fuel, and even if you wanted to, all of the replacement components it would need for its entire lifetime, and it could just sit there and make power. You don't need giant pipelines of stuff. You don't need trains of coal. You don't need all these things. So that actually, we hope, allows it to be more widely deployed in countries which don't necessarily have their own natural resources. Because it's a thing that you can build somewhere, as opposed to like you need to continuously pipe in gas or you need to continuously train in coal. So we're not going to promise it's going to be the cheapest ever, but we think it should be.
Red microphone.
I'm Bob Hershey. I'm a member. Could you tell us a bit more about some of the units that are already completed?
Other tokamaks?
Yeah.
Yeah, sure. Like I said, more than 100 tokamaks have been built in the world. There's, let's say, a dozen currently operating like large-ish facilities. There's a bunch of small ones, large-ish ones. There's one in Japan, the JT60SA, one in Korea, K-Star. K-Star is very, very similar in geometric size to SPARC, but less than a quarter of the magnetic field. 2 in China, East and HL3. There's a couple in Russia, T15M, I think. I get the name wrong. 2 in India, 1 in Germany, ASICS Upgrade, 1 in France called West. There's East and West, which is great. 1 in the UK called Mast Upgrade, 1 in the US called D3D in San Diego. So there's, 1 in Switzerland called TCV. So there's a number, these are all run by academic research institutes. There is one other privately operated tokamak in the UK from a company called Tokamak Energy. It's a smaller machine, kind of trying to demonstrate some of the science. So far, the 2 highest performing tokamaks in terms of fusion generated were JET in the UK, that shut down about a year ago, and TFTR in Princeton, and that shut down in the 1990s. Hopefully that's like a reasonable overview. There's a lot of tokamaks. I could like talk an hour about just different tokamaks, but there's a bunch of them.
Okay, I think we're going to the blue microphone, Robert.
Robert Thompson, I am a member. I'd like to follow up on the first wall question that was asked earlier, and I'm just interested in a little bit more information about the first wall life cycle. You mentioned that you expect to replace the first wall every year or two, but you're talking about having tens of thousands of these devices around the world, and while it won't be as long-lived as fission byproducts, it is still radioactive, and I wonder how you're going to dispose of this. Is there any way to recycle it?
Yeah.
What's the plan there?
Yeah, it's a good question. So after you run this machine, it does become activated. Basically, it's like the metal in the wall, after you hit it with enough neutrons, becomes activated material. You have to be thoughtful in how you handle it. It's very different than spent fission fuel, but it is activated. It's possible to recycle them. These are things that would be recyclable in like tens of years, not tens of thousands of years. So like it's not tomorrow, but it's kind of like within like a reasonable human lifespan. You could like go from like something coming out of a plant to something that you can put into a new plant, which means that like it is a very manageable amount of stuff. And the stuff is like very safe to be near. You don't want to like maybe like touch it, but it's safe to be like nearby. You don't need to like do anything too crazy with it. So it's like an aspect of the plant that you need to design around the byproduct material, but it's a very, very different class of material than spent fission fuel. It's much more similar to like what you'd see coming out of a hospital, like hospital waste from radiation therapy or something like that.
Red microphone and maybe 1 or 2 more. Got a question from Maria there in the middle. But the red microphone.
Hey there, Jeff Colomb, non-member. Thanks for your talk. So my question is about what you can do with a lot of electricity. I believe that the refinement of weapons-grade uranium requires a lot of electricity in one place. Training AI chatbots is putting a lot of pressure on electricity supply. Are there killer apps down the road where if we could generate 100 times more electricity, we could do totally new things?
Yeah, it's a great question. At a high level, one of our near-term goals is that we would like fusion to look like a coal power plant minus the coal part for a couple of reasons. One is the grid knows how to deal with that. You don't need to rebuild the whole grid if you can take out coal boiler, put in fusion thing. So there's fusion as an energy source in terms of like what does it look like for the grid isn't going to be like completely different. But going to your question of like, what if we had way more energy and it didn't pollute stuff and you could like manufacture it? Like desalination, like you could have way more clean water in the world. Industrial processing of stuff, like right now, like a lot of like industrial heat processes are like really energy intensive just to manufacturing. As you say, like AI data centers. One of the reasons we want to go to Virginia is like Virginia has a huge boom of data centers right now. There's multiple like hyperscaler companies that have like fully contracted entire nuclear power plants to power stuff for them. There's definitely other. I mean, the classic like long-term what could you do with fusion is like interstellar travel. It's like how could you possibly store enough energy to go to another solar system? Like no chemical energy possibly would work. There's no way to get enough stored energy. Fusion could work. Like the energy density of the fuel, the quantity mass of fuel you have to the energy that comes out in fusion is like millions of times more energy dense than chemical stuff. So that's obviously a bit further away in time, but like if you wanted to travel interstellar, it's like probably fusion's the only way to do it.
Well, since you're talking about data centers, I guess I'll interject the question du jour, which is to what extent has AI changed your design approach and actually your design, if at all?
Yeah, I say like AI, we use AI, machine learning, like more broadly, in select aspects of the design. It's not like we like go ask ChatGPT, please design fusion power plant for me, and it just tells you how to do it. Not quite there yet. But there are data-driven like machine learning models that we can use to accelerate simulation codes. We run like a big set of simulation codes, collect all that data, use it to train some kind of machine learning model, and then you can run in real time something that theoretically, nominally would have taken a day to run. So we have like much better control models, much better design tools, quality control. Even like some of our magnet manufacturing, we use machine learning to like spot defects, which isn't like the most exciting, oh my God, like AI usage, but like it massively speeds up how we inspect our material. And in the control as well, like, there's something called reinforcement learning where you can like, if you have a good enough model of the tokamak, you can build a controller for it using machine learning to help like better control the plant. So, it hasn't completely changed everything that we do, but there are a lot of like cool, really beneficial applications within Fusion to apply like modern AI, like machine learning technology.
Do you have a training set based on or some substantial fraction of all the other tokamaks?
Yeah, I mean, for different aspects of the plasma, there are some training sets, yeah. But there's wildly large amounts of data, and like getting it all into a form which is easily consumable sometimes is
No surprises?
Yeah, right.
All right, we'll have a last question, red microphone.
Okay. Of course, all of us want cheap energy in order to, fire.
Name? Are you a member?
No, yeah, Maria Zemankova, member, and we, of course, all of us love cheap energy, right? And clean and all that. I was intrigued by the schematic you had there when you had the molten salt around the boiler. So are you really actually running the molten salt reactors? Because the purpose of molten salt is to take the energy from the boiler, whatever is in the boiler, and run the turbines or whatever and produce electricity. So isn't that really what you're doing?
Yeah, I mean, the molten salt, it's a heat transfer fluid.
Yes.
Correct.
Yeah.
I mean, even to the
Doesn't
extent...
matter what's inside, but the way it works is because of the molten salt, right?
Yeah, like most often fission, when they're a molten salt reactor, they literally have fuel dissolved in the molten salt. So like the salt is, parts of it are fissioning. Okay. We are not doing that. Like we are using it purely as a heat transfer fluid, not as like the actual
from
fuel.
The boiler, what's in the boiler.
Yeah, and I mean, so some concentrated solar actually is molten salt. So they have like a big array of mirrors, a tower. Some of those use water steam directly, but some do use molten salt. There's like half a dozen plants in the world that use molten salt purely as a heat transfer fluid. So for us, it like produces tritium, but primarily it's the heat transfer fluid.
The heat transfer, yeah. Okay.
Yep.
That's what you're doing, yeah.
Okay, I got
it. Understood, yeah. Okay, thanks.
For sure.
Last question, blue microphone. This is
Thank you.
The last question.
Jason, I am not yet a member. You mentioned that this, the technology that enabled this entire design to be practical was the next generation of magnet technology.
Yep.
What is the status of the next generation after this? And is there some theoretical limit that would prevent us from having Mr. Fusion from Back to the Future someday?
Great question. Next generation, so like maybe next generation magnet technology is a cool question. There's a lot of talk of like room temperature superconductors. That would change a lot of stuff. It wouldn't actually help fusion that much because really what you want is really, really high magnetic field superconductors. The temperature is a nice side benefit, but like the field that you can operate at is like the key advantage. But there are other technologies that could be a big deal. Like even higher magnetic field often actually we think will come down to higher strength structural materials. Like if you could make unobtainium, which is infinitely strong, you can make the magnet much more compact. Because like at some point, even if your superconductor is infinitely good, your magnet is one tiny superconductor with a giant block of steel to hold it together. So like next generation structural materials, the fundamental limit on deuterium-tritium fusion specifically is you make these neutrons that are quite fast, 14 MeV neutrons, and you need to you need to absorb their energy in some amount of stuff. And with like the best stuff that you can use, molten salt or like some things that are a little bit thinner, that's like order of magnitude a meter of stuff that you need from whatever you're making the fusion in to the first like structural, like the first like thing that might get damaged from neutrons. And so like with deuterium-tritium fusion, the fundamental like size limit is like how quickly can you stop the neutrons? There's some ways around that. My like science fiction version of this is like if you had neutron star material and you can make a tiny little layer of that, that's like crazy dense. In which case like you can have like a super, super, super little thin, very, very narrow layer of neutron shielding material. Our materials team keeps telling me to go away when I say this. But in terms of like crazy ideas that would make your machine way smaller, like incredibly dense neutron shielding material. There are other more advanced fuels for fusion that make fewer and lower energy neutrons. Almost any kind of fusion makes some neutrons, but you can make fewer and lower energy. That could reduce the size of the machine as well. But there are some limits that you run into at some point. All that is to say, like, there's a lot of innovation in the world, and like this is kind of our creative thoughts for today, but 10 years from now, maybe there's another great thing that happens, and like maybe we don't know what that thing is today, but we figure out what it is, and that takes us to the next innovation. So,
what a great way to end your talk. Thank you very much.
Thank you.
So before you go, we have a few gifts for you. Whoops. We have a copy of the announcement of your talk, framed for you to display or not, and a copy of volume 17 of the Bulletin of the Philosophical Society of Washington, which includes a lot of the formative papers and a couple of histories and a list of Henry speakers and things like that, which is fun to read on a plane or something. Great. And a rosette emblazoned on the side with the symbol for induction or inductance, which Excellent. Is named the Henry for our founder, Joseph Henry.
Excellent.
So thank you so much.
Thank you so much for having me. This has been great.
Great.
Thank you.
And before we adjourn to the social hour, we have just a few closing remarks. My first one is all of you who said that you're interested or you want to join, please do so. You can use the cards at the back and the QR code. It's not much to it. You fill out a form, pay your $75. Your application will be reviewed. If you have a genuine interest in science, we will be very happy to welcome you to the society. Remember that all members are invited to the reception and dinner with the speaker preceding each lecture. And you get a signed copy of volume 17 of the PSW Bulletin. So please feel free to join. I love to be able to announce new members at each meeting, and I look forward to announcing yours. Our next talk will be the 94th Joseph Henry Black Tie Dinner and Lecture, meeting number 2518, and it will be on June 27th. The speaker will be Jason Dworkin. He is a senior scientist for astrobiology and the project scientist for the OSIRIS-REx mission at NASA Goddard Space Flight Center. and he'll be speaking on the analysis of samples from the asteroid Bennu that were brought back to Earth by the OSIRIS-REx mission return. There are some surprising results if you haven't read about them, and I think he may be even announcing some things that haven't been published yet. So mark your calendars and don't miss out on this closing gala event of the year. Other upcoming lectures. The last lecture for members of this spring semester and for the 2024-25 year will be the annual meeting and business report on July 18th. There will not be a lecture, and this is for members only. The first talk of the fall semester will be Will Marshall, who is the CEO and founder of Planet. And for those of you who don't know, Planet has a constellation of small sats that photographs the entire landmass of the Earth twice a day and has been a revolution in seeing changes that occur on a daily basis and has played a role in the unfortunate many conflicts that are going on now. Others are listed here. I'm not going to go through them. Before we go, let's thank our crew who ran our cameras and set up our room. And who will undertake the arduous task of packing all this up and bringing it back to where it came from. And with that, I will accept a motion to adjourn the meeting. A second. All in favor? All opposed? Meeting is unanimously adjourned to the social hour. Enjoy the refreshments in the back.